Um, so simple things like representing an image and image processing involves like augmenting the image, editing the image, or doing things to the image at a low level. And when I say low level, I mean like uh, extracting information or doing things to the image that isn't really doesn't involve abstract information. It's just like you're changing the color of the image, for example, or you're changing it from colored image to grayscale image, etc. And then mid-level computer vision will involve a little bit more complicated algorithms. These these algorithms like go into how can we connect images to other things. So how can we associate images with other images? How can we associate image with the real world, with the real 3D world, and things like that? And how can we extract depth from 2D images and video streams? And then lastly, I'll go into machine learning. And so in this section, I'll mostly be focused on deep learning because that's kind of where that's kind of what I'm most familiar with when it comes to computer vision in ML. So yeah, and then I'll list some modern applications that I think are really cool, and that might motivate you guys maybe to start looking into computer vision even more. Okay, so where computer vision started, right? So this was like about 55 years ago. There was this professor at MIT who I believe is the one who wrote this paper, who kind of had the idea of creating a visual system, right? And to him, it was like a summer project. So he got some of his students and said, let's create a significant part of a visual system, right? That's what's quoted in the paper. And so some of the goals that they mentioned in the paper was subjects that we're still working on today, right? So dividing pictures into regions, which is image segmentation, identifying objects, that's what we call object detection today commonly. And then differentiating between textures is like, what I mean by that is basically identifying different textures, like knowing that a brick wall looks much different than a plain brick colored background, right? So, and even using textures to actually identify objects too. And so, yeah, now 55 years later, we're still working on this. And I'm not saying that there isn't good solutions for this. There's so many good solutions for a lot of these subjects I'm going to talk about. But the thing is, like, a lot of the solutions have specific applications, right? So each application usually, like, there's not really a general solution to object detection, for example. There's not a general solution to segmenting images or a general solution to identifying types of textures. So that's why computer vision is exciting, because it's constantly evolving, and it seems like every other week, like a new research paper comes out that goes over a new algorithm that does something way better than the last algorithm did. So yeah, okay. So the reason I included the Wikipedia definition here is just because I wanted to say something about it. So again, like keep in mind, like, I'm an undergrad student, but this is what I think, right? So the Wikipedia definition says, computer vision is an interdisciplinary scientific field that deals with how computers can gain a high-level understanding from digital images or videos. From the perspective of engineering, it seeks to understand and automate tasks that the human visual system can do. And so the last sentence I definitely agree with. It does seek to do that. But you see, when and I could be wrong, right? But I'm just telling you guys what I think. When the definition says that deals with how computers can gain a high-level understanding, well, I think computer vision definitely allows us to extract high-level information from photos and video streams. But when it comes to understanding, I think when you use that word, it starts to bleed into perception and cognition a little bit, which are different fields in AI on their own, or not necessarily in AI, but they're different fields on their own, where those fields, I don't know much about, but from my understanding, those fields are concerned with replicating human thought process, right? And that, I think that's why, since they use the word understanding, it bleeds into a little bit perception and cognition. And that's I brought that up because I think that's a mistake that a lot of people do, maybe unconsciously or not knowingly. They use they say, oh, AI tries to understand. No, AI, I don't think AI tries. Well, certain areas of AI, like perception and cognition, yeah, they replicate the human thought process. So maybe you can say those kinds of systems can understand. I have no idea. But when it comes to computer vision, from my understanding, is concerned with mostly extracting the information, and then you can decide what to do with the information afterwards. Okay, so low-level computer vision. So let's start, right? So images are, if you're not aware, images are represented by small units called pixels, and an image is usually a rectangle of these pixels, right? So it kind of looks like a grid, and each one of these small pixels is represented by an 8-bit integer. Okay, so 8-bit integer, if you're not familiar with what a binary is, basically the maximum value that an 8-bit integer can hold is 256. Okay, so it's 0 is defined to be black, so that must mean like the highest value which is defined to be white, or like the highest value which is white is 255, right? So the highest value that a pixel can have is 255, but since we started at 0, it's still 256 different shades. The way that these images are stored in a computer, or let's say you want to load an image in a Python script and start playing around with it, most likely this is how it's going to look like. You're going to have it in or the most common way for typical hobbyists that would do this is just to load it in as a matrix, right? I mean, even researchers in the field, like this is how most people, if you want to augment an image manually or by hand, this is how you would do it. You would load the image in, and it would be represented by a 2D matrix. So the way a 2D matrix is represented in a computer is just using a 2D array, and that's exactly what this is down here. And if you're not aware what a 2D array is it's just an array where each element of the array is a one-dimensional array, and then each element of the one-dimensional array is an 8-bit integer. Okay, so yeah, and then you can start playing around with the augmented and put it through a object detecting model or whatever you want. So colored images. So pretty similar to grayscale, except where we have 3 color channels. We call them channels, or they're called channels. And the color channels are blue, green, and red. And then the combination of those you can see at in this bottom right, on the bottom right, and this is the color model. So I'll talk more about this cube in a second, right? But first, I just want to say each channel in the image is its own 2D matrix. So then this image is represented as a colored image is represented as a 3D matrix that always has 3 channels or 3 2D matrices within it. And similarly to black and white images, it can also be represented in an array in a computer, where the array, instead of being 2D, it's now 3D. So a 3D array consists of, or this particular 3D array would just consist of 3 2D arrays within it as the elements of the outermost array, right? And so if we look at the color model here, the blue-green values are, so let's say we increase all the values, right? If we increase everything, we're going to end up with white. And that's what this cube is saying here, right? If you make everything maximum, you're going to end up with white, right? If you make everything 0, you're going to end up with black. So if you slowly decrease all the values at the same rate, then you're going to be like going through this cube to the other opposite corner, which should be black. It just, you can't really see it in the diagram, but it's black. So what if we increase only 2 of them? Well, if we increase red and blue, we end up with purple. Okay, makes sense. If we increase green and red, but we keep blue to 0, then we end up with yellow. I was actually surprised when I learned this, that green and red make yellow. But I guess light color works differently than paint color, right? I mean, usually you don't get that if you mix green and red in paint, right? But yeah, Anyways, so there's another color model that I want to talk about, which is HSV. And so the HSV model, its three values are different. So the value that controls color, it's only one value that controls all whatever hue you want, right? Which you can think of as just the actual color. And that's the hue value. And so the value or the value called value is actually the bright. And so it's interesting how brightness is separate from saturation. So saturation is how much white light is in the pixel. So if you look at the top here, this hue of this teal blue hue, if you decrease the saturation all the way, that's like adding lots of white light. So it's basically a white pixel. And if let's say we decrease the value, right? If you decrease the value all the way, then there's no light, there's no brightness at all to the pixel. So it's going to be black regardless of where it is in the cylinder in this model. So a lot of the times this model is actually represented using a cone where it's pointing downwards. So the bottom of the cylinder would be just 1 point, because if you have a value of if the number or the value of your value is 0, then it doesn't matter where you are on the bottom of this cylinder, it's going to be black. And so this is useful when you want to separate the information of color and brightness. If we go back up here, right? If we have white, like let's say, for the lack of a better word, the color white, right? If we have the color white and we want to decrease the brightness consistently or decrease the shade of it, we'd have to change all three values of this pixel. Whereas here, if we have white and we wanted to decrease the value, we just we want to decrease the shade or the brightness, then we would just lower the value or the value that's called value. I don't know why it's called value, but yeah. So also, if you want to change the color, if you want to go from like orange to some like, I don't know, some weird purpley blue, then you change that. You do that by just changing the hue. Whereas here, you definitely have to change 2, if not 3 values. So yeah, that's those are the 2 color models. Okay, so now let's get into how can we actually extract information or from an image. And one way you could do this is by applying an operation called a convolution, which is just taking this kernel. So what a kernel is a smaller, it's like a smaller image you could think of, but it's not really an image. It's actually just a matrix that holds certain values. And it's applied to the input image in a certain way. And the output of that operation is one value, which gets placed into one pixel in the end. So let's go through that operation. What is this operation, right? This operation, which is called a convolution, is an element-wise product. So you multiply every element with the corresponding elements in the same position of the area of the image you're overlapping it with. And then you sum up all of those multiplications, or you sum up all of those products, and that's the pixel value you end up with here. And so there's something about this example, though, that's not accurate, actually. If you really think about it, how many times can we fit this kernel on this input image? The number of times we can fit it on this input image is actually less than the number of pixels there are on this input image. So how can these guys actually get an image of the same size as the input image when the number of pixels or the number of placements of this kernel, which results in 1 pixel each, is less than the number of pixels on the original image? And so that's kind of why I wrote up this example too. So if we apply this kernel here to every one of these positions, every possible position, you see that the image decreases in size. And so what happens here for a 3x3 kernel, you lose the border. And if your kernel is bigger, you lose more of the border. So here, because this image is originally so small, it's like less than half the size, right? But really all it is that you lost the border. If you think about it, like if you remove the border, if you remove the border of the pixels of your computer screen, you're barely even going to notice because it's a huge image essentially. So yeah, so this is the convolution operation. So this particular kernel is called the identity kernel because it actually just picks up on the same pixel values. So if you see this, there's a 1 here, which corresponds to the center of wherever you place this kernel, and then everything around it is 0. So let's look at the red box. If we multiply the everything around the center pixel, which is 0, if we multiply everything around it with 0, then so far we have 0. And then we also multiply the center by whatever is in the kernel. Sorry, I just got a weird message there. If you remove the center, if you also multiply the center, which happens to be 0 here, you get 0 in the top left. So this top left box, this kernel applied to the top left box results in 0 on the output image. So let's shift it over and look at one that results in actual value. So if we multiply 1 by 0 and then plus 0 by 0 plus 2 by 0 plus 3 by 0 plus 0 by 0 plus 0, 0, 4, 0, everything around 3, 0, and then 3 by 1, then we just end up with 3. So it's called an identity matrix because it just literally copies over the pixels. And so let's look at a kernel that actually detects a feature. So here's a larger image where the top half of the image is value 10, which is like a gray value basically. Or if you're on a grayscale, then yeah, it's a gray value. And then the zeros basically represent blackness. So there's an edge here, basically. That's what I'm trying to say. There's an edge right here. And we want to try to detect it. So we can do this using a kernel. If we place values in the kernel like this, what this is saying is basically, well, the pixels that are in this position will be counted a lot. The pixels in the middle are counted, they're not counted. I'll explain why in just a second. And then the pixels below the edge or below in this position are counted negatively. So we actually want them to be as close to 0, if not 0, as possible. So, and that's because this detects an edge that goes from a high value to a low value, right? So we want this bottom to be low as possible for the resulting output to be as high as possible because these are negative values, right? And then since these are just positive ones, we whatever is on the top here, we just want it to be as high as possible. So let's apply this, right? So if we apply this to the top left corner, the values in the third row are the same as the values in the top on the first row. So they're just going to cancel out. So you're just going to get 10, 20, 30, and then you're going to get 20, 30, 30. So you're going to 20, 10, 0. Once you subtract it, I don't know why I said it like that, but basically these result in positive 30, these result in negative 30. And the zeros in the middle, the 10s in the middle are not counted because of the 0. So if we shift it down, where now these negative ones are going to be placed here where my mouse is, and the ones are still going to be applied to the number 10s, right? So 10, 10, 10, you're going to get a result of 30. And because here now we're at a lower shade or a different pixel or a lower pixel value than these ones, that basically we're going to get a high number as the result, which happens to be 30. So another thing is if we shift that down even more, these ones are still applied to these last row of 10, right? And so we still get 30, right? And so this is something to point out, right? Like you get 2 rows of 30s here, and that's because, well, how what do you define as your edge? Is it this row of 10 here? Is this bottom row of 10s, or is it this top row of zeros? Like which one do you pick and why? You can't just say my edge is you can't just say my edge is the line that's in between zeros and 10s, because that's not a pixel. Like you can't really point at that in an image. You can't point in between 2 pixels, right? So we decide that both of them technically count as an edge. And so it makes sense that there's 2 rows of zeros here. Yeah, and so so this can actually be displayed as an image. And when you display this as an image, the resulting image is basically it's going to have like white lines on it. So this row of 30s and this other row of 30s are basically a line, like on the grayscale value. So it's going to highlight the areas where the feature of the kernel detects are. So wherever they are in the image, it's going to highlight those. So you're going to get like, if there's like a circle in your image, the output is going to be like the outline of the circle. And yeah, this is just one. So what if we want to detect going from bright to dark in the opposite direction? What if we wanted to like vertical edges, diagonal edges, circles, angles or curves, or there's so many things you can want to detect. So this is just one type of kernel. So in fact, I'm gonna copy this link here and I'm gonna send it to you guys. So this link, this website, I encourage you guys to go on it and play around if you want, but I'm also just gonna paste it in the chat here. So I'm gonna paste it in chat. Feel free to go and check this out, but I'm also gonna show you guys on the screen myself as well. Yeah, I gotta watch the time. Okay, so this basically this website just goes through like different types of kernels. So you can see here basically these are pixel values. It actually shows you the pixel values of this image, and then it allows you to pick a kernel, like let's say like a blurring kernel. This is what a blurring kernel would look like. It applies it to the image, and you can see here every single position of the kernel on the image. And you can even make your own kernel here, and you can see the effects that it has on the resulting image. So that's kind of cool to play around with. So let's move on to the next bit. Oh yeah, so before we move on, like basically we wanted to say that you can also do convolution on colored images. It's just rather than just a two-dimensional kernel, you'll need a three-dimensional kernel. And it still results in one pixel because we still end up adding all of the corresponding multiplications. Okay, so here's a Colab demo that credit to Jay because he helped me with this. He kind of wrote this demo and saved me a bunch of energy. So again, I'm gonna paste this in the chat. And yeah, feel free to play around with it, but I'm also gonna go through it on my screen so you guys can just sit back and watch if you want. Right, so I'm just gonna make sure we're running on the GPU. Okay, cool. So these libraries here, they're just tools that help us to display images, load images, change their types and things like that. So yeah, so the image, we're getting an image from the internet, and now we're gonna look at it and play around with it. So we're just loading the image, and let's look at its shape, right? So this is like a 512 by 512 image, so it's a square image. So notice it's only 2D. And so if we look at the data type of the image, it's uint8, which basically means it's an 8-bit integer that's unsigned. And so unsigned basically means if you're not familiar with binary, we're able to use all of the bits to represent the number. We don't need to reserve any bits for the sign. If you print the image, you get a matrix, just like I showed you guys in the slides, which is not surprising, right? And then it also just tells you the data type. So if we show the image, if we display it, so here's the image. It's just some peppers. Okay, so let's look at the colored version of it. So you'll notice now we have 3 channels. And that's because since this is a color image, we need 1 channel for each color, right? Red, green, blue. So the data type is still uint8, makes sense. This is a little bit confusing. You can't really tell that it's like a 512 by 512 by 3 image just by looking at this. But I mean, you should be able to just, in practice here, you wouldn't really print the whole image to get its shape. You would just, you just kind of print color.shape or image.shape. So yeah, that's what it looks like in colored form. So let's do something with this image, right? Let's try to augment the image ourselves, like manually, just to get a feel of how we can play around with an image. So what we're doing in this line is we're literally just adding the value 100 to the image. And then we're making sure that all of the numbers are still within 0 to 255. And then let's see what we get. Right. So there's the original image, and there's the image after adding 100. Literally just the same image, but brighter. Right. Cool. So here are some other kernels you could use for other types of operations. I'm going to read them all because I'm running low on time. But let's look at a convolution operation. So I believe this one uses the kernel used here is the edge finding kernel. So this kernel here, it finds edges. Oh, whoops. This kernel is used for finding edges. And you can see how well it does here, right? And so just a quick overview. Basically, in this for loop, what we're doing is we're just iterating over every element in the kernel and in the image portion of the image that we're overlapping, and we're multiplying all of those, and then we're adding them up together. Basically, that's what this for loop is doing. Okay, back to the slides quickly. Wait, did I miss anything in the demo? Let's see here. Nope, that's it. Okay, cool. So mid-level CV, this is one of my, some of my favorite subjects are in this section. So histogram of oriented gradient. Okay, so this slide, I'll attempt to explain what an oriented gradient is, and then I'll explain the histogram part in the next slide. So an oriented gradient is basically, so the way we can take a gradient in the X and Y direction of a pixel. So let's say we're focused on pixel P and we want to take the oriented gradient of it. We can do that by basically subtracting for the X values, subtracting the pixels from the left and right sides, right? So so traveling in the X direction, we just subtract the values before and after the pixel. So in this case, we get 60 going in this direction. And similarly for Y, we get 60 going in the upward direction. And so since they're the same values, we end up with a vector of angle 45 degrees. So these X and Y arrows are vectors. And when you combine them like this, you can get their magnitude just by using Pythagorean theorem. And then using just simple trigonometry, you can also get the angle of the resulting vector. And that red vector is the oriented gradient. So let's look at this, right? This guy over here. In this first image, these are the gradients in the X direction, and then these are the gradients in the Y direction. And you'll notice that in the X direction, there's a lot of vertical lines, which is weird, right? Even though this is the X direction. Well, that's because in the X direction, the most drastic gradients are going to be across vertical lines. So these are actually a bunch of gradients across one line. So it's like, if you look at let's say the edge of this image, right? This is going to have like a bunch of gradients going left and right, like all over the edge of this image here. And that's why you see vertical lines in the X gradients and then horizontal lines in the Y gradient. You're not actually seeing horizontal lines. You're actually just seeing vertical lines across a horizontal edge, because the edges are what have the most drastic gradient. So this is what you get when you combine them. You see this guy kind of looks more normal than these two guys. So the information that this holds is just a bunch of vectors. Kind of looks like a vector field, right? So each one of these vectors just represents the gradient of the pixel in that location. So if we take a portion of the image and want to represent it in a smaller compact form, we could literally just count how many vectors point in each of the directions. So we categorize them like this, using this wheel here, this pi thing. Every vector that basically falls between this range, this top range here, we count as like pointing upwards. Say that's like 90 degrees or something. And then every vector that's pointing in this range, we count as going like diagonally, like 135 degrees. So when we collect them into 8 different classes like that, we can display this is basically a descriptor describing how many vectors are pointing this way in that local region, how many vectors and their magnitudes are pointing bottom right diagonally in this region, how many vectors pointing. So you can see that there's not many vectors that are pointing to the bottom left. And if there are, their magnitudes are probably small. So if we do that for each kind of quadrant, this is like one way of describing this portion of the image. If we do that for the whole image, we get something like this. But before I talk about that, so these are essentially basically histograms because we're just counting the item of the number of occurrences for each category, right? And so if you look at this image, you can see that like in the blank spaces, they look like stars, and that's because every vector direction is almost equal. So it's like it looks like a star, right? But on the areas that have like detail, they look more like lines, and that's because most of the vectors in the area of interest have the same gradient, which makes sense, right? And this is a really good way of compressing an image, but still retaining high-level information. And this is actually used to be used often for object detection. I'm not sure if it's still used, but basically, if you think about it, you have way less information in this image. So, but it still holds like the general information, like abstract information, like you could still see the outline of the cup, right? So you can, if you put this through an object detecting model, for example, you have to do much less computing. Like the input dimension of this image is much less than the input dimension of the image on the left, right? And that has to do with grouping the vectors like this and describing a local region just with one histogram. Okay, so the next thing is, so stitching images actually uses what we just described, right? So these by the way, they're called hog descriptors for short, HOG, hog descriptors. So stitching images actually uses hog descriptors. So okay, one method for stitching an image is basically detecting key features that you'd also be able to detect in another image, right? And so if you find some of these same key features or unique features in another image, the same ones exist, you could just overlap them according to like lining up the features of the both images, and then you could like stitch it that way, right? But the key is whenever you find a unique feature, you have to describe it in such a way that if you find it in another image, that's like maybe your hand rotated a little bit, or you're zoomed in a little, or you're zoomed out more, or the lighting is different. Right, I want to talk about lighting. So if the lighting is different, for example, then you'd still need to be able to describe the feature in the same way. So if you see it in another image that's a little bit different, you can say, oh, this is the same feature. So let me just go back real quick. I just want to say why we were using gradient. So we're taking the difference, right? We don't really care about the value of them. Like this could be like 0 and 60. It would still be a difference of 60. And that's because we care about the gradient and not the actual lighting. Not because let's say you took a picture of this guy at sunset versus like 2 p.m. The lighting is going to be much different, but the gradients on his face are going to be generally the exact same. I mean, not the exact, but generally the same. So this is like invariant towards lighting. And so the key with stitching images is you need to find features using a method that's invariant to lighting, invariant to rotation, zooming in, zooming out, and yeah, things like that. Basically, things that would prevent you from being able to identify the same feature. So some of the algorithms that can do this for you are surf, sift, and orb. Originally, I was going to go into the sift algorithm a little bit in this talk, but I thought, there's already a lot of content and it's a little bit complicated. So if you guys want, I could do like a part 2 if you're interested. Well, we could talk about that later. So, okay, optical flow. So optical flow. So what you're seeing here is when this guy's moving his hands around, these vectors, this red stuff that you're seeing are vectors, and these vectors are pointing in the direction of his motion, the motion of his hand. So it's pretty intuitive, right? Like, so every time you move your hand, the system should display vectors that point towards the motion of your hand. And this is useful for many applications. Also, do you notice in the background there's like no vectors? Well, there's no vectors. They're actually just vectors of value 0. Let me just check the chat here in case anybody asks something. All right, I think we're good. By the way, if oh, Toss, if I missed your question, is it always wrong to say that AI can understand? Well, going back to that, yeah, as I mentioned, like there are areas in the field like cognitive AI that like seek to I haven't really studied this at all, but from my understanding, they seek to imitate the human thought process. So I don't really know if you would classify that as understanding. I don't know if I think that might be a little bit subjective. I mean, even the AI, the definition of AI itself is kind of subjective. Like, I was gonna get into this later in the talk, but like a long time ago, like about 50, not a long time ago, but, when sorting algorithms were being developed, they used to uh, consider those as AI, like sorting algorithms. So, but nowadays, I think most people wouldn't call that AI, although that's still arguable. I'm not sure, right? So, I think the definition is pretty subjective. But yeah, I think there are areas of the field that seek to make AI understand, right? So I wouldn't say it's always wrong to say that. So my answer would be no, in short. But yeah, so the link to the slides is at the very top. If you scroll up, they're there, and then I'll also send another link by the end of the talk of the slides. So yeah, that's what optical flow does. So let's move on to the next slide. So this is also optical flow, but so on the image on the left here, just ignore the green lines for a second. That's kind of something else. But I just want you guys to see the video stream that we're computing optical flow on. And then the video stream on the right is the optical flow vectors, but encoded using colors. So if you look at this color wheel, if you just get all of your vectors or get every single vector and place its starting point at the origin. So any vector that's pointing to the top right should be colored like purple. And that's why these cars that are moving towards the top right are colors like purplish red, because that's their direction of their optical flow vectors. Similarly, for the cars that are traveling to the bottom right, they're yellowish orangish, which makes sense. Bottom right here is yellowish orange, and then the cars that are in the top that are going to the left are like a teal blue, and to the right they're like a red color. And so this kind of ties into the next slide, because I want to say that you see how the cars in the front are much brighter than the cars in the farther away. You can actually extract depth information from that, because we kind of know, like, from the perspective of a 2D image, right? Objects travel faster when they're closer to the camera than farther away. And that's not like physically traveling faster. That's just like according to like if you track the object on the image, they travel faster when they're closer to the camera. So we can use that to extract depth information. I don't know how often that people actually use that, but it is a algorithm that exists, or there are techniques that take advantage of that. So this is another way of extracting depth from information. So what structured light is if we display a known pattern of light onto an object, and oh, somebody said something. Let me check a quick one time. I understand the color mapping, but how can you track depth through color? Oh, okay. Let me make that clearer. Sorry. So I didn't mean actually color. What I meant is that the objects of the same color are changing in magnitude. Yeah, I must have misspoken there. So the magnitude of the vectors here are much higher than the magnitudes of the vectors here. And that's because the purple here, it's still the same color purple, just dimmer. So also something that might confuse you guys. The center of this color wheel is white, but it really should be black, because the default color in the background here is black. I just couldn't find a color wheel with a black center, but some people even do optical flow but with a white background. So in that case, this would match and it would be accurate. But yeah, so just know that, like, basically the smaller the magnitude of a vector, the closer it gets to the origin. The origin should be black. So the vector should get dimmer and dimmer in color, but the same color if it's in the same direction. So like Tassif, I was like more talking about the brightness or intensity of the color than the actual color. The actual color doesn't matter as long as you're tracking the same color. If it gets dimmer, then you might be having an object that's moving farther away. I hope that's clear. So yeah, structures of light, right? So if we just play a pattern of the same of a known pattern, for example, light beams of the same width and same distance apart. And then we analyze like the resulting pattern of light that we can see through a camera, we can observe through a camera. We can kind of extrapolate some depth information from that, right? Like you can see that the lines of light drastically change in direction and shape and stuff wherever there's a huge change in depth. And if you can do that through multiple resolutions too. And so here's kind of a 3D model you can generate. So whoever generated this model, you should actually be able to like look at it and turn it around, and it's in a 3D simulation. So that's pretty cool. And if you rotate the model and keep doing scans, we should be able to generate like a really good 3D model using this method. Another really cool, entertaining subject is stereo vision. So, okay, first, what stereo vision is it's when a system has two cameras instead of just one. So your eyes are actually like considered like you have stereo vision, right? If you hopefully you have both your eyes, like then you have stereo vision, right? So you could see here that, okay, so what's really happening is one eye is seeing the object that you're looking at from a different perspective than your other eye. So you can actually triangulate like how far the object is. So when we display two images from two different perspectives on an image of the same scene right after each other, then you can kind of get a sense of depth here. And it's kind of cool. Like it kind of feels like, my screen is like turning 3D. And so you can see the objects in the background are moving much faster than this horse. So we could say that the objects in the background must be much farther behind or much closer in front of the horse. So we can extract depth information from it. So let's look at an example in more detail. This jaguar, right? Let's look at its eyeball. Its eyeball is not really moving much at all, but its nose is moving more than the eyeball. So, okay, the nose must be in front of or behind the eyeball. And the shrubs in the background, or like the tail or the feet in the back, are moving way more than the eyeball, even way more than the nose, right? So they also must be in front of or behind the eyeball. And so even more though, right? You can even do more. So you could say that if you really look closely, the legs in the background or the shrubs in the back, they're moving in the opposite direction of the nose. So that must mean one of them must be behind the eye and one of them must be in front. Now, how would you actually say which one's in front and which one's behind? I'm not sure. I haven't studied this subject too much, but there's definitely good amounts of depth information you can extract from this, man. And this has been studied. I just haven't studied it myself, but it is a really cool subject in computer vision. What else was I gonna say? Let me read the comments here. Yeah. Can you see stereo vision to track moving objects? Can you use stereo vision to track moving objects in video? That's a good question. Well, I'm not too sure about that. Stereo vision to detect objects, because you can actually output the information of stereo vision in a colored stream. Like for example, you can say really fast things, really far things are colored black, and the closer they are, the colored white. So I guess you actually could track an object based off of color, because if it has a high value, meaning it's closer to the object, closer to the camera. Let's say it's a really white circle. That means it's an object that's close to the camera and it moves. You should actually be able to track it based on the pixel values, right? Or based on where it is depth-wise. But that's only accurate to an extent, because if then it starts moving around objects that are the same depth as the camera, then you might get a little bit confused. But that's definitely possible, actually. That's definitely possible if you have like an object that doesn't have much surroundings around it, like a tennis ball, for example. Yeah, so that's a good question. I like that one. Yeah. So yeah, that's really all I want to say, I think. Yeah, about this. Oh, what I was gonna say is, like, before you can actually do this depth information analysis, you need to be able to associate the two images together. So that's a challenge on its own. Right. So let's get into high-level computer vision. Okay, so let's just talk about the big picture, right? So how does computer vision even fit with AI, machine learning, deep learning, all these terms, right? So you might already know this, or you might be familiar with this hierarchy, but basically artificial intelligence, which I kind of talked about how it's kind of a subjective thing, um, is a field that kind of encompasses machine learning, which encompasses deep learning. So deep learning is a subset of machine learning, which is a subset of AI, right? And now computer vision, it has subjects that don't really have to do with AI or machine learning, which is what I was trying to, which are most of the subjects I explained in low level and mid level. But it has subjects that do intersect with deep learning, machine learning, and AI. So yeah, that's a good thing to know. So ML versus deep learning, right? So machine learning achieves to, or it's a way to achieve AI, right? That's really what it is. And specifically, or more particularly, right? It does this by like learning things or trends from relevant data. And when I say function here, basically, you could think of of any task as a function. Like if you want to detect whether there's a cat in your image or not, you can just put the image into a model, and the model you could think of as a function, because you have your input image, you put it through the model, and the output is a yes or no, right? It's kind of like a binary thing. So like that task can be modeled as a function, especially since your number of pixels is like it's not infinite, like it's limited, right? You can use all that information. Um, uh, and when I say from relevant data, I mean like usually you want good distributions of data to use, right? So for example, if you're trying to detect a cat in your image, if there's a cat or not, so yes or no, then you won't just include pictures of non-cats, right? You'd also include some pictures of cats to train it as well, right? Or similar, like also you won't just use like 2 pictures of cats and then 10,000 pictures of non-cats. That would be a bad distribution, right? So that's kind of what I mean by relevant data. And ideally, we want to do this with minimal human intervention. Let me just look at the time here. Okay, good. We want to do this ideally with minimal human intervention. And then once we have a trained model or a trained system, we want to use that now since we put so much effort into it. We want to now use it in the real world and actually make real world predictions that need to be made, or predictions that or problems that don't have solutions, and actually apply those models. And deep learning is a way to do that, what I just said, or all that, right? And again, these aren't perfect definitions. I'm not even trying to define what these are here. I'm just explaining kind of what machine learning entails, what deep learning entails. So deep learning achieves machine learning. And so it achieves machine learning, or it learns from the relevant data sets using artificial neural networks. Usually with deep learning, the more data, the better. I'm not sure if that's the case with every machine learning algorithm though. But yeah, maybe you can search that. I'll leave that as an exercise. Okay, so what is a neural network, right? Everybody's using this term. It's the hype in AI right now. What is a neural network? Okay, so this is what a neural network looks like. Okay, so now you know that much. So a neural network consists of layers, right? Each layer has a number of nodes. The first layer here, which we would say is the layer, usually by convention is just the layer on the most left, is our input layer. So this would be like a number of pixels that we have from our image, for our image, usually more than 3. And then the layers here, blue and green, are called your hidden layers because those are what do computation. And the output layer also does a computation based off of the last hidden layer too. But we just categorize it differently. We say this is the output image. The output layer, which can output more than one node. I just have it in one node here for simplicity. So I want to talk about just a little bit about how this is computed without getting too like mathy. So let's look at A11. A11 is basically the first node in the first layer, because we would call the input layer the 0th layer, and then the first hidden layer as layer number 1. So layer 0, layer 1, and then node 0. sorry, node one. There's no node zero because it's just a convention thing, basically, because we can what happens is we can represent these neural networks in matrices, and you start indexing matrices from one, not zero. So that's why we start with zero from the layers, but we start with one from the nodes specifically, just because we use matrices to represent them. So it's just a convention thing. So the way A11 is computed is it basically multiplies every single connection, because each one of these connections is you could think of it as a weight, and that weight is just one. So A11 cares about the first feature one factor by a factor of one, and it cares about the second feature by a factor of two. It cares about the third feature by a factor of 1.5. So it multiplies every corresponding feature with every feature with its corresponding weight, and then adds all those up. But that's not everything, right? So if we look here, so let's call this just Z1. Just bear with me for a second, right? Z1 will be what I just said, the weights times the corresponding input values. Okay, that's all good. Now, what is this B value? This B value, I mean, you can honestly train neural networks without it, but it's helpful. It's also a learned parameter. So these red parameters, which are weights, are learned by the network. Initially, they're just random weights, the random values, but they're learned. And B is also usually learned as a learned parameter. And what the purpose it serves is to you can think of it as it normalizes the data, because if your data is like 1004, 1005, 1006, it would make much more sense, and it would be more useful to use that data if it was just a 4, 5, and 6. So it's just the distribution of the data relative to itself is the same. It's just everything is just shifted over, right? And that's a way to normalize the data. I mean, if you want, you could search more about this. It's just called data normalization. But typically, that's what B serves. There's other reasons, I think, for having B, but you can honestly train a network without it. And oftentimes people do. And then A would be that, okay, 7.5, but put through a function called the activation function. Now, the activation function can really be any nonlinear function, right? But there are particular ones that tend to work well. And, I was going to go into this as well, but I didn't want to talk too much about activation function. Like, I don't want to get too into the math for this talk, just because I want to keep it targeted to as much people as possible. But yeah. So, Tassif, why is it important to normalize data? Well, you could not normalize the data, but you'd want to normalize it. Well, I think it makes computation easier. I think you wouldn't want your numbers to diverge. In other words, because what if those numbers just keep getting bigger? I think so. This problem is called like the exploding something problem. Basically, each time you go through a layer, you multiply numbers by coefficient. Whoa, doesn't that mean they could just keep getting bigger and bigger and bigger? Yeah, thank you, Jay. That's what it's called. It's the exploding gradient problem. So it just basically means that as you propagate through the network, if you allow large numbers to exist, okay, that's okay. But what happens when we can't even represent those numbers with the data structures we have or the data types we have, right? So we want to control that. And we want to normalize the data between different layers. If you want to search this too, it's called batch normalization. So batch normalization is another technique of normalizing the data between layers, so that the actual magnitude of the values that come out of each layer is independent from the previous one. Not independent, like when I say independent, I mean I don't think I should have used the word independent. Not independent, but it doesn't get affected by this exploding problem or exploding gradient problem. Right? So, okay, that's enough of that. I need to continue. But yeah, I hope I answered your question. So it's put through. So then Z11 is put through its function called the activation function, and its purpose is to introduce nonlinearity. Why do we want nonlinearity? It's because if you look at this, right, if we just take Z11 and then put it through the next weight, like let's say this line here for A21, what would happen to that? Well, we're just applying another coefficient to it. And if you just multiply this thing by another coefficient, then it's still, then what's the difference between doing that and multiplying it by a coefficient of, the same thing? Like if you just basically distribute the coefficient to each one of these numbers, because the coefficient is 2, then what's the difference of doing that and multiplying 1.2 by 2 and then 1.5 by 4 and then 2.2 by 3, right? So what I'm trying to say is your model overall would still be linear. If you just kept propagating through the model with linear operations, your whole model is still linear. Okay, so I'm spending too much time on this slide, so let's move on. By the way, keep in mind that the things that are learned are these weights, these red values, and B if you have bias terms. Okay, so Tensorflow Playground. This is like a cool little playground that Google made, because Google is the one who made Tensorflow. So I'll send this in the chat. And I encourage you to play around with this too, but I'll just play around with it just for a very small amount of time, just because I'm running out of time.
Mostafa, I think you accidentally directly messaged me the link.
Oops. Chat to everybody. Okay, there we go. Sorry, guys. Okay, so there, you guys should have the link now. Thank you, Jay. So here you can, you guys should be able to see my screen because I'm still on Safari. But so here, if you look on the very right first, this is our distribution of data. And you can choose between all these, but let's just stick with this one. So each data point has 2 features, right? It's described by X1 and X2. And so that's our data set. Okay, that's good. Okay, so this is the actual diagram of the neural network. You can see our inputs are X1 and X2, each feature of every data point, or each feature of a data point. Let me just make this one hidden layer for now. These are our hidden layers. Now you can see each hidden layer computes a different feature. So each hidden layer, it computes it by basically multiplying the weight by multiplying a weight by with every previous feature in every previous feature, right? Just like we said, just like we saw on the slide. So this shape here, or this distribution here, or this feature here, is basically a combination of 0.23 times this feature and 0.28 times that feature, which kind of makes sense. Like, look at this feature, right? It has orange in the bottom left. These two both have orange in the bottom left and blue in the top right. So this one also has blue in the top right. So yeah, that's the intuition behind that. But as you propagate through the model and as you go deeper, it kind of gets harder to understand why those features look like they are mentally, and we'll get into that. But let's train this and see what happens. Okay, so it actually converges. So you can see here, it learned pretty well, right? Like, this is a simple task, arguably. And sorry, I think there's somebody that has their mic on. If you wouldn't mind muting it, that would be awesome. Oh, oops. Okay, guys, so when I went on that website to describe the kernels, it looks like I also directed that to Jay only. I don't know why every time I go on Zoom messages, it only directs it to Jay. Okay, so he just resent the website that I went on to explore the kernels. So you guys have that in the chat now too. And I'll post everything in the end. Will the recording be available? Yes, it's being live streamed now on YouTube, I believe. And that live stream will also be uploaded. And I'm recording it on my end as well, just in case. So this will be available. Okay, going back to the example. So yeah, this model converges. So let's look at what's going on here. So the output here is a combination of all these hidden layer features, right? So just multiplying this by -1, or this feature by -1, this feature by -1.6, sorry, -1.7, -1.6, 1.9, negative 0.47, right? So it's basically this output here is a combination of all those, but it's not a linear combination because we have an activation function, and this one happens to be 10h. But again, I'm not going to go into that. But so what I want to point out is that look, there's one feature that it doesn't really care that much about, and that could describe kind of why. Maybe that could explain why this kind of looks like a triangle, because it's getting most of its information or most of its weights. The highest weights are only on 3 of the previous neurons, right? So if we take out one of those neurons and retrain it, it should still be able to do okay. And it does, okay? So that's awesome. Okay, cool. And again, it kind of looks like a triangle, and that might be because this output is a combination of all these 3 neurons, which are each one have kind of a linear bisection of the data, or yeah. So what I want to do now is show you something more complicated. So let's add a bunch of hidden layers and a bunch of neurons, and let's look at I just want to look at the features that are being computed in between the model, and just show you guys how this gets really hard to conceptualize in your mind. This might just take a second, but I want to watch this thing train. Oh, it's actually diverging. Okay, let me pause this. This might be a good example. So this is what I mean by diverging. It's really doing bad. It can't learn anything at all. Yeah, diverging. So what I mean by converging is when, so the test loss and the training loss should be coming closer together over time, like asymptotically, if you know what asymptote is, which basically means that training loss and test loss should be getting closer and closer and closer, but they'll never really touch each other in most practical cases. But here they're just getting farther and farther away. So this model is actually performing really badly for some reason. Maybe I have too many neurons. Let's remove one here, one here, one here. Still doesn't seem to be doing that well. Well, anyways, what I wanted to point out is look at this, for example. This function is starting to get pretty complicated. So it's really hard to visualize what deep learning models are doing within themselves, or within what the neurons are computing and how they are. So a large part of deep learning actually is explainability of AI, or explainability of deep learning. That's a really important, in my opinion, really important section. And you see how it's starting to compute really complicated things. That's because we gave it more hidden layers and more neurons to use that keep adding more complexity. And because we added all that complexity, it's able to compute more complex models, right? Or sorry, more complex functions. So if I pause this right here, you can see it's actually almost doing it. It kind of has a part of the spiral here, but yeah, you might need to leave it training for longer, or add more neurons or whatever. But yeah. So yeah, you guys, I really encourage you to use this, to try it out, try different data sets. This one's easier, this one's easier. So try different data sets, get a feel of how this works, and maybe look into some really high level libraries for deep learning, and which we'll actually get into soon. So if we go to the next slide here. So convolutional neural net, right? So before I show you a full picture of a convolutional neural network architecture, let's kind of get an idea of what one layer in a convnet looks like. One layer in a convnet would be just a number of convolutions, like we mentioned earlier. So these are just kernels being applied to this input image through the convolution operation, right? Just like I talked about in low-level CV. And if you remember, when we applied there was one slide where I showed applying a kernel to a colored image, and you end up with a one-dimensional output. And that's because we still end up adding everything throughout the layers, throughout the channels. So if we do this with 2 kernels, we're going to end up with two images, and we can just combine those, and we say that this is the output of this current layer. And usually we have many layers, right? Or sorry, we have many kernels. So we end up with an output image that has like 64 or 128 channels, for example, if you had 128 kernels. So before we get to the full architecture, there's just one last operation that I want to tell you guys about, which is max pooling. So max pooling, basically, the idea behind this is just to reduce the dimensionality of the image, but we still retain some kind of information, right? And so what's happening here is basically we're applying this filter, or you also just called a kernel, a 2x2 kernel to the image, but we're having a stride of 2. And then that allows us to never touch the same part of the image twice. And the reason for that is because we want to analyze each section of the image and reduce that somehow. This is called max pooling because we're just going to take the maximum value of the blue section, place it here, maximum value of the green, place it here, and so on, right? And if you had a filter that's 4x4, then you have to have a stride of 4x4, or sorry, a stride of 4 in both directions, which is why there's 2 numbers here. So then you never touch the same part of the image. And the reason for this is because we kind of care about if this was a layer, if this image, right, was in a layer that detects, for example, a curve, we just you might only care about where the curve is in the next image, and you don't really care about where the curve is not. You just kind of care about where the curve generally is. So if this image in the middle of being put, or like this is one of the layers of the convolution, right? One of the output layers, one of the outputs of one of the layers in the convolution, where 9, let's say, represents a high probability for there to be a curve in that area. Well, we just care about the fact that there's a curve in the top left general area. So we can reduce the dimension that way by still keeping information. And please feel free to ask. Okay, there's a lot of comments. If you use activation function in the hidden layers, it could possibly confuse the model. No. So what I mean by compute complexity is that the model itself would be able to compute more complicated functions. If the model was just fully linear, it wouldn't be any different than computing a linear function, right? So allowing the model to compute nonlinear things will allow it to learn nonlinear things. That's really what I was getting at. So putting complexity in the model will allow it to learn complex functions. I know a lot of models fail to converge if you use the sigmoid 10H in the middle layers. Those activations should mostly be used in the last layers to normalize. Okay, that's a good point. So maybe the viewers can do that, try that on their own time then. So if you use activation function, yeah. And the vast majority of neural networks I've seen, they use ReLU. Yeah, that's true. Again, so I didn't want to get into much about activation functions, but ReLU is usually the standard for hidden layers. And then for the output layers of a neural network, you usually use other activation functions. Like if you're really interested and you want to search this up, things like sigmoid or softmax or other 10H, etc. Yeah, so thank you for clearing that up, Jay. Just wanted to clarify, reducing the dimensionality is important to make calculations as complex so the GPU can handle the model, right? Oh, I see. Thanks, Jay. So there can be many reasons we want to reduce the dimensionality, and I'll get into one of them right here. Yes, that is one of them. If we can reduce load on the CPU or the load on the GPU, but still retain the same information, that's ideal, right? We're saving money right there. We're saving money and time. Saving money by requiring less hardware, exactly, right? So, but also there's another reason here. So if we look at this, let's say we apply convolution on this image that has n1 number of kernels. Now we're going to have n1 channels, okay, which makes sense. We already know that. We apply max pooling. It retains the same number of channels, but it reduces in dimensionality, in height and width only, not in the channel dimension, only in the height and width dimension. Now we apply another convolution, and notice that even on the convolutions, it's reducing. It's reducing in size, and that's because we're losing the border, as I mentioned in the beginning. And then now, once we added this next convolution, we had even more channels, n2 number of channels. And we keep doing this, right? And we keep doing this until we basically have each channel is like one. You can think of it as basically just one value. If each channel is one value and we have like a linear thing like this, then that's basically the input that can be just fed into a regular neural network. So the job of the convolutional neural network is to extract the visual features, and we'll see even more of that in the next slide. And then once you have a number of visual features and where they are generally, you can then put them through the neural net. Also, one thing that I didn't really explain, the things that are learned in a convolutional neural network are the values of these kernels. So rather than just having layers of neurons and then learning the values, the coefficients for the neurons or the weighted connection, we learn the values that would go into the kernels and what kernels would extract the best information. You don't really know as humans. We can't really design the best kernels, so we let the model learn what the best kernels are for the particular data set, because that's really hard for a human to do. So we're no longer hand designing kernels. We're letting the model learn the kernels from the data. And that's the whole point of machine learning, right? So yeah, I think that's kind of all I wanted to say in this section. If anybody has questions, feel free. Yeah. Okay. So when I said that the job of the convolutional neural net is to extract the visual features, this is kind of what I meant. In the beginning, it usually gets simple features. The kernels don't have much to work with yet. Or that's not really the case, actually. It's more like kind of, this is how the convolutional neural networks end up learning. Because if you want a complex feature in the end, you kind of have to build off of simpler features. So in the beginning, what usually occurs is you learn simple features like this: edges, curves, circles, etc. And then in the mid-layer features might look something like this. So you actually have eyeballs, noses. I hope this is clear. This is I know this is a blurry image, but you have basically pieces of a face. And then you can actually detect the whole face from those. You can see, oh, well, how many eyes are there? Or, what's the probability of there being a nose in this area of the image, etc. And then you can predict what face is in there. Same thing for cars, same thing for, these are just a bunch of examples. But the point is, they all actually compute pretty much the same initial fundamental features, basic features. And that's because, well, an edge is an edge, right? Whether it comes from an elephant or a car, like an edge is an edge in the end of the day. So what most likely happened here is these people actually just use the same exact features on the other models. So what you can do is, rather than training the whole model, you can freeze this section. You can freeze the beginning section of the model, and then only train the rest of the model to pick up on different features. So you save more computational, you save more computing power that way, or you basically, you need to compute less, basically. And so yeah, this saves a lot. And it's like, well, why would you learn the features of an edge all over and over again? That's inefficient, right? You should just use the same edge features, because an edge is an edge, circles a circle, etc. And there might be cases where you're initially, the features in the beginning are very unique to your problem, and yeah, in that case you would need to train it from scratch. But if you can, why not train it from a pre-trained model? Okay, let me answer this one question and then we'll get to this demo. I see. So in convolution operations, you learn the best kernels, while in fully connected networks, you learn the weights, correct? Yes, that's exactly correct. You learn the best kernels, meaning you learn the best values to put in the kernels. So the kernels can make good feature extraction. And in a neural network, yeah, you learn the weights, which are just you can think of them as just the connections from one neuron to the next. Okay, let's get to this demo, and I'm going to send this as well. If I can just copy this and make sure I send it to the whole chat, to everyone. Okay, I think that's to everyone. So this is a Google Colab node. So what Google Colab is, it's a platform that Google developed, where they provide like a programming environment for you where you can, it's really a Jupyter notebook, you can think of it, but where Google provides a computing capabilities. So you can like make the runtime into a GPU or even a TPU. And yeah, so yeah, I didn't explain that before, my bad, but yeah. Oh, I think I already sent this in the chat actually, but yeah, it's whatever. Run. Okay. Let's let this run. Okay, there we go. So I'm gonna scroll down, skip all this. We already went over this. Oh, right. So this is the oriented gradient section. I didn't go over this just because like, I don't know, like I think going through this code might be a little bit complicated for this talk, so I kind of left it out. But it's here as a resource for you guys. If you're interested in like looking through the code for oriented gradient, please like feel free to look through it, play around with it, do anything you want. Yeah. So convnets. So okay, let's get to this example. So the data set we're using here is the MNIST data set, which is it consists of 10 different classes. Each class is a handwritten digit. And they're grayscale images. So there's 28 by 28 by 1. So let's run this first set, see what happens here. So the data here, what you're seeing is data. This is the data set, right? This is just 10 items from the data set. Each row is one example, one training example, where the first element is the training table, and then the rest of the values are the pixels in the data set. And since this is a 28 by 28 image, or these images are 28 by 28, we have 784 pixels in total. So if you keep scrolling, you'll see more than just zeros. You'll actually see values. And so there's zeros because the background is actually black typically. This is just white. I think this is just white just I don't know, just so it looks nice, I guess. I'm not sure why that's white background and black numbers. But you'll see here shortly, we're going to display some of the pictures. But yeah, let's look at the training sets and the test flow. Okay, cool. So number of training images is 20,000. We got that just by getting the length of the training data. And the number of training, the shape of the training data is this. Just by extracting it from the file, we haven't done any processing yet, and we might need to do processing before we input it to the convnet, because convnets need data, need to have the images as actual images to like height by width, not just vectors. So yeah, this is just to get an idea of what the data looks like, just get a feel of what's going on. You should always know what your data looks like. And so, yeah, this is what I was talking about. We're just reshaping the data to look like 28 by 28 by 1. And the last one here is just because we only have a channel of 1, but we still need to specify the channel. And the negative one here basically just tells the computer, these are what I want for these dimensions, and the computer can figure out what the first dimension should be, and the computer should be able to figure out, just because that's just one thing to find, right? It's just one parameter to like one missing variable, right? So yeah, let's run this. So yeah, that's just us transforming the data, preparing it to be put through the convnet. So here's where we actually show some examples. So you can see, right, the zeros, initially you saw a bunch of zeros in the images because zero is black. So you can see here, mostly it's black, and it's white or grayscale wherever the number is written. Okay, so let's create the convnet now. Okay, finally, like the exciting part. So what's happening here is we're using this framework called Keras, and Keras is a really high-level library that basically you can create models really quickly in Keras, but you have a little bit less control versus frameworks like TensorFlow or PyTorch. If you haven't heard of those, there's just other machine learning or deep learning used for deep learning frameworks. So the first line is just telling Keras we want to start a model that's sequential. Sequential basically just to say that the layers are consecutive after each other. So model.add. So this is where we add the first layer. Okay, this is where the actual thing, magic is happening. So this is just one line, right? This is just because every time we hit a comma, we just hit enter just to make the code look nice. But this is really just one line. We're just adding a layer with one line, which is pretty awesome, to be honest. So we're telling it we want 64 filters. and the size of those filters are 3 by 3. The stride is 1, which is just normal stride. I believe that's the default. The activation, we're making it as value. Again, like, I'm really sorry, guys. I didn't go much into activation functions. I wish I did now, to be honest. But yeah, I'll leave that as an exercise for you guys to do. Go research activation functions and why people use different activation functions. And then the input shape is, we just specify 28 by 28. That's the original input. So, and then we add a max pooling layer, right? We talked about this, right? Basically, this just reduces the dimension of the height and width, so that eventually we just get a long, like a really huge number of channel 3D matrix that we can basically flatten and convert to a model to a neural network. Otherwise, we'd be doing way too many convolutions before we get to that stage. And sometimes having a huge model doesn't help. It would be much more helpful to use an efficient model. For a simple task, use a simple model. For a complex task, use a complex model. Anyways, next line is the second convolutional layer. Again, we're doing even more filters. They're still the same size, 3 by 3. The stride is the same, and again, the same activation. And then we add another max pooling. And then this is the fully connected layer. Now, I forgot to mention this, but basically, this is called a dense neural network because all of the layers, every neuron in one layer is connected to every neuron in the previous layer, and so on. So when you have that full connectivity, if we have just one layer, then it's called just a fully connected layer. Oh snap! What is happening? Oh, I have two open at the same time. Anyways, so this is what this flattening operation. The flattening operation actually just prepares it to go into the dense layer, basically. And then the dense layer is made up of 10 different neurons, and that's because we have 10 classes in our data set. And so this is actually going to be our final layer, right? And we're going to get basically these 10 different neurons on the end of the neural network are representing the probability for each class to be the actual value that's shown in the image. And softmax is another application, activation function that's used it's used mainly just for output, for classification models especially, because what this will do is it'll convert all the values, because the values initially are like, let's say random, I don't know, it could be bigger than 1, for example. So what softmax does is it makes it so that every value in the final dense layer, if you sum them all up, you end up with 1. So you can actually consider every single value as an actual percentage probability. So the probability of 9 being the number in the image is like this much % probability, for example. So yeah, it just makes it nice so that we can look at these things with, through a probabilistic type of probability, basically. So here we're just compiling the model, that's fine. So this is where we're actually training it. And so we pass in the train model, basically the examples and the labels. And then we also pass in batch size. So batch size, you don't really need to worry much about this. In short, we're just telling the model how many different images we want it to compute at once. But I don't know, I don't really want to get into that right now. Basically, it just means we can actually stack a bunch of images on top of each other. And if we just stack the kernels on top of each other as well to match their dimension, we could just do a bunch of convolutions at once rather than one convolution at a time. But if you don't understand what this is, it's not critical to know. It's not really critical to know what a convolutional neural network is. Epochs is the number of times we wanted to train on the specific data set. And this is just a programming thing. We wanted to give a certain output. And the validation data set is our test data set, basically. And it's called validation just because traditionally, or how things normally work, is you have 3 data sets, one for training. Because researchers usually develop multiple models at the same time. So they use one data set to train all the models, one data set to test every model and compare all the tests against each other, and then a final data set to compare the model they ended up choosing with the rest of the models, because your data set that you're comparing different models with could have some bias in it. So it's just It's just basically a final measure to compare your model with real world data rather than using that data to compare with other models. Anyways, that's not really relevant either. But if you have a question about that, yeah, you can feel free to ask. Here, let me answer these questions actually. I know we're actually like literally about out of time. Filters, wait, sorry, if this is repetitive, how define the size of the filters? How did the filter parameter determines how many kernels? Yeah, so the filter parameter is the number of kernels the number of different kernels we're applying. So like we're doing one kernel for one type of edge, another kernel for another type of edge, or another kernel for circles. So it's literally the number of kernels. Yeah, that's what the filter parameter is. Kernel size, yeah, just like Jay said, it's the size of the kernel. Yeah, we need to wrap this up. So let's run this code already. Let's run this. Okay. So we're gonna watch it train here. Oh, what happened? Input 0 layer conc2d is incompatible. Oh yeah. Yeah, I think there's just a missing. There's just a type. There's a missing one here. Okay, there we go. Compile it and fit it. So here we're actually fitting the model. See, it's going to output the result of each epoch, and you can see it's giving us the loss, which is basically how bad the performance of the model is for every epoch, and as well as the accuracy. And then the validation loss and the validation accuracy are for the test sets, which we gave in as validation data. And since this is, by the way, since this is just one model, we don't really need 3 data sets like I mentioned, right? But if we were comparing models together, then we might, but that's a different story. So this here just prints a graph of the loss. The loss decreases over time, over every epoch we perform. Accuracy, this just prints the same graph, but for accuracy, how the accuracy is increasing over every epoch. The reason that the validation accuracy is higher in the beginning, so usually your training accuracy should be higher than your validation accuracy, because your training is what the model has already seen. Validation is it hasn't seen, but it's kind of from the same distribution of data. So it should still do decently well on, right? So, but the reason that that validation, which it hasn't seen, is more accurate than what it has seen in the beginning, it's just because we initialize the model randomly. So that's just really a fluke. It's an anomaly, to be honest. But you can see how, accuracy gets better and validation is usually less than training accuracy. So this is the final test loss and test accuracy. And so this last code cell here, what we're doing here is we're literally just printing the predictions that the model got wrong. Okay, so we already know the model is like 98.5% correct. Okay, that's cool. We know the model works well. Actually, it'd be good to visually confirm that. But just to make it interesting, we're printing the things that it got wrong and seeing what did it get confused, right? So out of the 1,000 samples, this is like how many, like 15 or 20 or whatever images we got wrong. So label 3, which we can tell it's a 3, but it guessed as a 5. Okay, maybe I can see that happening. But yeah, you can see like prediction is 8. Yeah, that's not really. Prediction is 0. Or wait, sorry, I'm reading them wrong. Prediction is 5. Prediction is 9 for this one. You can actually see how that could happen. Prediction is, wait, are the labels at the top? Yeah, labels are at the top. So the label is at the top and of the actual image. So label for this one is 6. Prediction is 0. You can kind of see how that can happen. Label for this one is 9. But it predicted 8. Label is 2, but it predicted 7. Again, you can kind of see how that happens. So our model is doing okay. Just the really weird written numbers that are not performing well. So yeah, feel free to edit that notebook and do whatever you want to. Okay, really quickly wrapping up now, right? Modern applications. And honestly, I wanted to talk about this the most, so it kind of sucks that I ran out of time. But for those of you who are still here, thanks for staying this whole time, honestly. Sorry for taking this much time out of your day. But so, okay, so for agriculture, firstly, right? So these are like 2 applications that I put down here, right? If you look at the right hand first, these are this is detecting basically diseases in the plant. So this is like plant disease detection. I actually tried to do this myself one time. Um, and yeah, so that's one application. So farmers usually, if you're a new farmer, especially, you might not be able to detect, or you might not be able to tell what disease your plants have. So you might spray like a concoction of pesticides, which is not good, right? This is not good for eating, especially. So it would be useful to have a model that can identify particularly like exactly what the disease is, so it can use the correct pesticide rather than overdosing with so many pesticides and then like killing other animals in the area and harming humans even and stuff like that. And then here just like autonomous drones like spraying pesticide or water or whatever that is over the plants. But yeah, that's for agriculture. Healthcare. This is the most interesting example I found. So you could see here, this is the input images. And then, so this is a brain scan, right? This is a brain scan. And these are all, this is the prediction that the model ends up making. But I'm assuming, so the model goes through a system of filtering out the detections that it's the least confident with. And then you end up with like something like one detection here. And it's actually pretty accurate. So these anomalies in the brain, I'm guessing are like tumors or something wrong with the brain. And then this model is able to actually detect what parts of the brain are defected, which is really cool. Like, yeah. So retail and manufacturing, this is cool too. So if you guys might have heard, like Amazon opened a store, I'm not sure how long ago this was, but where you can shop with zero interaction with anybody. You can basically put items in your cart and it has a vision system to scan the item as you put it in the cart. And so it charges you on the spot. Well, it doesn't charge you on the spot. It basically adds it to your cart on the spot, your virtual cart. And so once you leave the shop, somehow they can detect that you left. And then every item that the cart observes, it'll charge you for. So that's really cool. This forklift here, I was talking to a company in the US, a startup company, where they're designing autonomous forklifts. And that's something that when I heard that, honestly, it was so obvious. Like that's like, duh, we need autonomous forklifts, right? But I never would have thought of that. There's so many applications like that where it's such a genius idea, but like at the same time, like how has nobody thought of it before? This is genius, right? I don't know. I just think this is so cool. Autonomous forklifts is I think going to be huge in the future, especially because then you don't have to hire a forklift driver, which can be expensive. Generally human labor is expensive depending on what country you're in. Oh, also for autonomous drones. So I was also talking to some startup in Toronto where they're developing a bunch of autonomous drones, like a large number of autonomous drones. Basically, just they're developing an autonomous system to plant trees right all over the place. And the interesting thing is, most of their customers are like companies that want to they just want to pay a cheap amount to plant a bunch of trees, and then so that they can say that they went carbon neutral. So I kind of thought that was funny. Basically, so there's a large market for that. Basically, large corporations are willing to pay money just to be called, carbon neutral, which technically they would be, I guess, if they plant enough trees. But yeah, I just thought that was a funny thing. Yeah, and finally, autonomous robotics. I mean, every one of the above, almost every one of the above examples had autonomous robotics, right? Like this, agriculture, and a lot of other types of agriculture. Like if you make an autonomous, like what they call tractors or whatever, that would be considered autonomous robotics. These are autonomous robotics, especially actually the forklift is an autonomous robot. If you could somehow make an autonomous shopping cart, that would be autonomous robotics. So autonomous robotics is huge in computer vision, in my opinion. And that's the part of computer vision that kind of excites me the most. And this is what I wanted to conclude with, basically, is that when it comes to computer vision, I think it hasn't hit its peak yet. We're still going to see a huge boom in computer vision, especially as people figure out how to make AI computing software, AI hardware, or hardware that is really meant to accelerate AI, smaller and less expensive and more efficient. When that happens, or the more that happens, the more of a boom we'll see in computer vision in the future, because there's so many ideas out there, particularly in autonomous robotics, that haven't been done yet, just because of costs. Like not everybody will be able to design their own custom chip for self-driving like Tesla did, right? So a lot of these self-driving companies are contracting other companies to make their hardware for them, which is really expensive. And companies that have good software support for their hardware, like NVIDIA, usually have expensive hardware. So, there's a lot of room for improvement within the AI hardware space. And I think that we're going to see a huge movement. And honestly, I hope you guys were got interested in computer vision from this somehow. I hope one of these topics, at least one of these topics, interested you enough to look into computer vision more. And yeah, it's honestly such an exciting field to be a part of. So yeah, thanks so much, guys. Honestly, for staying this long. Honestly, like it was advertised for 7.5 hours. We went on for 7 hours and 43 minutes. So yeah, I'm gonna stay for 5 or 10 more minutes to answer any questions. You guys can unmute your mics and ask me if you want. Also, I can write my email in one of these slides. And yeah, but you guys are the talk is over now. You guys are free to go. If you have any questions, feel free to stay and chill, hang out for 5 minutes. I can answer any questions you have. 7.5 hours. Oh, I meant 1.5. Yeah, it was advertised for 1.5 hours. So it's supposed to go to 7:30, but yeah, I went to 7:43. So honestly, like the 12 of you that are still here, thanks. Like honestly, I appreciate you guys so much. Thanks for staying. I'm